Module 2, Process Management. Process management is a fundamental function of an operating system, responsible for managing the execution of multiple programs or processes on a computer system. A process is an instance of a program in execution, and the operating system is responsible for allocating system resources, such as CPU time, memory, and input-output devices, to processes as needed. The operating system employs several techniques to manage processes, including process scheduling, process synchronization, and inter-process communication. 1. Process scheduling. The operating system schedules processes for execution on the CPU, taking into account factors such as priority, resource requirements, and user input. The scheduling algorithm determines which process should run next and allocates CPU time accordingly. 2. Process synchronization. When multiple processes access shared resources such as memory or input-output devices, the operating system uses synchronization techniques to ensure that access is coordinated and controlled to prevent conflicts or race conditions. This is typically done using locks, semaphores, and other synchronization primitives. 3. Inter-process communication. Processes often need to communicate with each other, either to exchange data or to coordinate activities. The operating system provides various mechanisms for inter-process communication, such as shared memory, message passing, and pipes. The process management function is critical to the efficient and effective operation of a computer system, ensuring that resources are utilized efficiently and that processes can operate concurrently without interfering with each other. Processes and threads. Processes and threads are both important concepts in the context of process management and multitasking in operating systems. A process is an instance of a program that is currently being executed by the operating system. It consists of an executable program, data, and system resources, such as open files and allocated memory. Each process has its own memory space and is isolated from other processes, preventing interference or conflicts. Processes are managed by the operating system and can be scheduled for execution on a CPU. A thread, on the other hand, is a lightweight unit of execution within a process. A process can have multiple threads, each running concurrently and sharing the same memory space and system resources. Threads within a process can communicate and share data more efficiently than separate processes since they share the same memory space. Threads also have a lower overhead compared to processes, as they require less memory and fewer resources to create and manage. There are several advantages to using threads within a process. For example, threads can improve application responsiveness by allowing different parts of an application to execute concurrently. They can also simplify programming and reduce complexity by allowing developers to divide an application's functionality into smaller, more manageable units. However, threads can also introduce complexity, such as synchronization issues when multiple threads access shared resources concurrently. Careful design and programming are necessary to ensure that threads within a process do not interfere with each other and that data is shared safely and correctly. In summary, processes and threads are both important concepts in process management and multitasking in operating systems. While processes provide isolation and security, threads allow for more efficient and concurrent execution of code within a process. Process scheduling. Process scheduling is a key function of operating systems that involves determining which processes should be executed on the CPU and in what order. There are several scheduling algorithms used by operating systems, each with its own advantages and disadvantages. Some of the most common scheduling algorithms include first come, first served (FCFS). In this algorithm, the operating system schedules processes in the order they arrive, with the first process that arrives being the first to execute. FCFS is simple and easy to implement, but can lead to long waiting times for processes with higher CPU requirements. Shortest job first (SJF). This algorithm schedules processes based on their CPU burst time, with the shortest job or process being scheduled first. SJF is optimal in terms of minimizing average waiting time, but requires knowledge of the CPU burst time for each process, which may not always be available. Priority scheduling: in this algorithm, each process is assigned a priority value, and the operating system schedules processes with higher priority first. Priority scheduling can be either preemptive or non-preemptive, depending on whether a higher priority process can interrupt a currently running process. Priority scheduling can lead to starvation of lower priority processes if not implemented carefully. Round robin (RR). This algorithm assigns a fixed time slice or quantum to each process, and processes are scheduled in a circular order. If a process does not complete execution within its time slice, it is preempted, and the next process is scheduled. RR is simple to implement and provides good response time, but may not be optimal for long-running processes. There are also many variations and combinations of these algorithms, depending on the specific requirements and constraints of the system. The goal of process scheduling is to balance the competing demands of system responsiveness, throughput, fairness, and efficiency, and ensure that all processes are executed in a timely and efficient manner.
Thanks for watching. For more information, like, comment, and subscribe our channel.